So sometimes you can cheat a little bit on these, okay? By cheating a little bit, what kind of graph is this? What kind of shape is this? It's a parabola, right? What does the equation of a parabola look like? Well, that's an x squared graph. What happens when we take the derivative of any parabola? It becomes a line. So we know this one is going to be a line, y equals mx plus b. And if we know we have a line, what happens when we take the derivative of a line? Just becomes a constant. So we know that this is going to become a constant. So that's going to help us figure out things on this graph. Now, when we are curve sketching, if we started with a parabola and we wanted to find, in this case, the local minimum, what would we have done? We would have taken the derivative and found out where the derivative was equal to 0, right? And when we found out that the derivative was equal to 0, that would have told us the x-coordinate of our local maximum or our local minimum. So first of all, you can see right here that we have our local minimum right there. So that means on our derivative graph, what's it going to equal to on our derivative graph? It's going to equal 0. So we know that our line, that's our derivative graph, has to go through that point. In fact, this one's, you could even figure this out exactly. You know, based on this 5, 0, and this negative 1, that this happens at x equals 2. So if you were sketching this, you would have started with your parabola, you would have taken your derivative, and you would have found out that x equals 2 is where you have your local minimum or local maximum. And you would have drawn the first derivative test, and you would have put 2 on there, and you would have found out that before 2, it had to be decreasing, and after 2, it's increasing, because that's what our original function is doing. Well, if it's decreasing here, what does that tell us about our derivative? Our derivative had to have been negative. And after 2, if it's increasing, our derivative would have to have been positive. So as far as our line goes, for our derivative, before 2, it needs to be less than 0, negative, and after 2, it needs to be increasing. So now we've sketched y equals f prime of x. That's in green. I'll square it in green so we remember that that one is in green, or maybe I'll label it as well. And now we need to do our second derivative. And our second derivative is just going to be a constant. In fact, it's a constant, and it's going to equal whatever you deem the slope of that line to be. So our green line, does it have a positive slope or a negative slope? Positive slope. So if we estimate that, maybe you think it has a slope of 1, maybe you think it has a slope of 2. Whatever you decide you think that slope is at, and any constant function is a straight horizontal line. So what we did is we looked at our original graph. We were allowed to cheat a little bit because we recognized it. We recognized it as a parabola. So then we knew our derivative would be a line, and our second derivative would be a constant. But then we used some of the same processes that we used if we were graphing a parabola. You would find your derivative and make it equal to 0, because that helps you find your max and your min. Well, since we know where the max is, we knew that our derivative was equal to 0 at x equals 2. Then because our graph was decreasing then increasing, we knew our derivative was negative and positive. So that helped us draw some more of our line. Now I'm not sure, based on this graph, whether or not my slope is accurate or not. I mean, we could have, if you wanted to try to be more accurate, you could draw a tangent at one of your points as best as you can and say, I think the slope of that tangent looks, does it look like a slope of 4 or 5? And if you think the slope is equal to 4, then you mark it at 4. If you thought it was equal to 5, you'd mark that point at 5. And that, too, would help you get your slope of your line. Because what your derivative is all of those slopes at all those different points of any tangent line. So here's our second graph. What kind of graph does this look like? A cubic. So if we're thinking that this is cubic, then our derivative will be some sort of parabola, and our second derivative will be some sort of line. Because the derivatives of cubics will always be parabolas, the derivative of parabolas will always be lines. So again, we go through the process. If I had my cubic graph and I was sketching it, the first thing I would do is find my derivative and make it equal to 0, because I want to find my maximums and my minimums. I can see right here that I have a local maximum here and a local minimum there. So when I would do my first derivative test, and this graph doesn't have a scale, but let's just count each of these as 1 just for now, just to help us visualize it. Can you see that at 0 and 4, you would have found our first derivative to equal 0? Yes? So what does that mean? That means that I'm going to have a point here at 0 and here at 4. Now our original graph goes up, then down, then up again. So based on that, what do we know about our derivative? We know that this section would have to be positive, this section negative, and this section positive. So what does that tell us about our parabola? That tells us that our parabola needs to look like something like this. We might adjust it in a bit, but we know that it had to be positive before 0, negative between 0 and 4, and positive after 4. If you were figuring out your second derivative, okay? Your second derivative, when it's equal to 0, is going to find what? Second derivative, when it's equal to 0, is going to find your inflection points. So if we look at our original graph, can you see that it changes from concave up to concave down? And it changes from concave up to concave down somewhere around here. Now here we make a connection between our second derivative and our first derivative. So if our second derivative is equal to 0 here, that means on our graph of our second derivative, our line will have an x-intercept there. Notice that wherever your second derivative is equal to 0, you either will have a local minimum or a local maximum on your first derivative. Because this is where language gets sometimes confusing. Does it make sense that your second derivative is just the first derivative of the first derivative? Okay, I'll say that again. Okay, your second derivative is just the first derivative away from your first derivative. Okay? And so if it's just the first derivative of your first derivative, that same idea, wherever I have, so here the green graph is my first derivative, so wherever I have a local minimum of my first derivative, I would have an x-intercept of my second derivative. So we have our inflection point on our original graph matching up with our minimum on our first derivative graph, which will match up with an x-intercept of our second derivative. Now, if we had our second derivative, and we're going to estimate that to be at 2, we would have found out that it was concave down here before and concave up after. If we thought of our second derivative as the first derivative of the first derivative, looking at our green first derivative, can you see that your green first derivative is going down and then going up? So as far as that goes, you would have had negative and positive. So we know that our line has to have a slope like this. Okay? And you could have got that negative value either from the concavity test. We see that before 2 it's negative, after 2 it's positive, or from the graph of our first derivative, that before 2 it's decreasing, after 2 it's increasing. Whew, yes? Okay. So now the first two were straightforward in that you started with the graph of your original function and moved to your derivative and then moved to your second derivative. Now we're going to mess it up a little bit more. Now we're starting with the graph of our derivative. And now we have to think, what was our original graph and what did it look like? So first of all, cheating a little bit, what kind of graph does this look like? A cubic. So if we had a cubic graph, what graph would we have had before that? A quartic graph. Great, eh? What do we know about our derivative is right here. We know that our derivative is equal to 0 at -2, 0, and 3. So if we were in the process of graphing our x to the 4, we would have, with our first derivative test, said, I know it's equal to 0 at -2, at 0, and at 3. And since this is the graph of our derivative, before -2, our derivative is positive. So that tells us that our original graph has to be increasing. Between -2 and 0, our derivative is negative. That means our original graph would have to be decreasing between those points. Between 0 and 3, we have positive again, increasing, then negative again after 3. Okay? So now we know that we're going to have a local maximum at -2 and a local maximum at 3. How high those are, can't really tell. I just know that that's going to be the case. And I know that it has to be increasing before that, decreasing after that. So if we just put some values on here, just see, since I don't know where they might be higher or lower than that, just to get a sense of what these values might look like. I'll randomly put some dots because I need those maximums to be higher than the minimum. That gives me an idea that my graph looks something like this. Some other things to check on our graph. Wherever our derivative graph has maximums and minimums, that means the second derivative will be equal to 0. So that's going to tell us that I should have had an inflection point here and an inflection point there. Does it look like my graph kind of has inflection points at those points? Maybe a little bit, not too bad. What we can't tell easily is how high our maximums are and how low our minimums are, right? But we're just estimating. So we're getting a general shape, and then if you wanted to check certain things, you could say, well, if I drew slopes on my green graph, do they match up kind of with the slopes that appear on my derivative graph? How close is that? And you could do some adjustments there. But right here, we're just trying to get the general shape of what our original function might have looked like. So now we're going to be working backwards again. Now we have the second derivative graph. You have to imagine what will our derivative graph look like, and then what would our original graph look like. Looking at this one, what kind of graph is this? It's a line. So it's y equals mx plus b of some sort. What kind of derivative would you need to get a line? A parabola. So this one will be some sort of parabola. And then what would we have needed to get some sort of parabola? Some sort of x cubed graph. Okay. All we know from this, all we know from this second derivative is we have an x-intercept right there. And if you were working through your derivatives, and let's just assume that that's at 1, just to make a number. What do we know is that after 1, our second derivative is positive. Before 1, our second derivative is negative. So what does that mean? Well, if we're thinking second derivatives tell us where things are concave up and concave down. So we know that our original graph is concave down there, concave up after. But we also know that our second derivative is the first derivative of our first derivative. Whew. So if our second derivative is our first derivative of our first derivative, what does a first derivative tell us? So here we have 1. Means if we only go back one step, we know that after it's positive, before it's negative, it means that our first derivative has to be decreasing and then increasing. So this point at 1 is going to be a local minimum. It's going to be a local minimum of our first derivative. So if I draw that in, some local minimum, increasing after, there's what our parabola could possibly look like. Now, having that parabola is telling us that we have 2 points. And those 2 points, well, they look like one's at 2 and one's at negative 0.5 or something like that. We know that it's negative between them and positive after. So if we went back 1, that means our function would have to be increasing, then decreasing, then increasing. And so at 2, we would have a local minimum. At negative 0.5, we would have a local maximum. At this point, I'm not going to worry about where those things are exactly. I'm just going to, let's put one here and one there for a local maximum and a local minimum. And then I know I need a cubic graph, so I need my graph go through there like this, and then went right through that inflection point. And it does look like that's where it changes concavity from concave down to concave up. And so there is an estimation, a sketch of what our graphs could have looked like. So at this point, would it have been wrong to have our values, our maximums and mins in different places? No, I'm not really concerned about that. I just want you to be able to think through the process of, if I have the graphs, what possibly could the original graph have looked like? So I'd like you guys to try this one on your own to have done for next class.